Welcome back. We're now going to talk about an improved algorithm that uses gradients and point evaluations of a function in the case where our function has smoothness. Recall that if our function was smooth, gradient descent was able to guarantee a convergence rate of 1 over t. But the lower bound that we saw gave something better, 1 over t squared. And if f was, in addition, beta smooth and alpha strongly convex, then gradient descent was able to give us kappa minus 1 over kappa plus 1 raised to the t, but the lower bound was improved again, square root of kappa minus 1 over square root of kappa plus 1 raised to the t, where again kappa is equal to beta divided by alpha. So we want to see if we can do better. The key idea here is a concept called momentum. So let's recall what the basic gradient descent algorithm is. Xt plus 1 is equal to xt minus eta times the gradient of the function that I'm trying to minimize. The idea of momentum is to include a term here that captures some aspect of where I was before, the direction that I was moving in. So the name is suggestive. So the idea of momentum is, if I look at the difference between xt and xt minus 1, this gives me the direction in which I was moving in before. We can even think about that as something like velocity, potentially. So the idea of momentum is to incorporate momentum somehow into the bounds. So we're going to see exactly how to do that in a little bit. So let me just draw a picture here. So the idea by picture is that we're at xt, and the gradient is pointing in this direction. The minus gradient. We're always following the minus gradient. When we get to xt plus 1, and the gradient is pointing in this direction. Again, minus gradient. Okay, so gradient descent would basically follow this path. But momentum is telling us that when we're going from xt to xt plus 1 to xt plus 2, that actually what we should do is we should include some multiple of this difference. So this vector here is this difference between xt plus 1 and xt. So this is my added momentum term. Okay, so this is the concept. And we're going to see that actually this is critical, and it will allow us in both of these cases of f being beta smooth and f being beta smooth and alpha strongly convex to close this gap and match the lower bounds. Okay, so let's start for the case where f is smooth and strongly convex. Well, the algorithm, which is sometimes called momentum, sometimes called accelerated gradient descent, is the following. So again, we're trying to solve minimize f of x, where f is beta smooth and alpha strongly convex. So the algorithm, let me write again gradient descent just so we can contrast. Gradient descent tells me that xt plus 1 should be equal to xt minus my step size times the gradient of f of xt, and typically we will take the step size to be equal to 1 over beta. This is what we derived. is a good step size. Accelerated gradient descent, or momentum, says the following. We'll initialize at some x1, and I also need an auxiliary variable called y1. So I initialize both of these to be equal. And then, after t iterations, I update y by yt plus 1 is equal to xt minus 1 over beta times the gradient of f of xt. This is just my standard gradient update for beta smooth functions. But this is yt plus 1. This is my auxiliary variable. It's not xt. Xt plus 1 is then equal to 1 plus square root of the condition number kappa minus 1 over square root of kappa plus 1 times yt plus 1 minus square root of kappa minus 1 over square root of kappa plus 1 times yt. So note that xt plus 1 is this convex combination between yt plus 1 and yt. So you see that xt plus 1 depends not only on xt, but it also depends on xt minus 1, because yt plus 1 is a function of xt, and therefore yt is a function of xt minus 1. So xt plus 1 is a function of both of those. It's a function of the past two iterates, and that's exactly where the momentum comes in. Now the guarantee that we can get here is the following. F of yt minus f of x star is less than or equal to alpha plus beta over 2 times my initial distance, x1 minus x star, times something that goes down like the square root of kappa. So we have improved from kappa to square root of kappa, which was exactly the gap that we had before in terms of order-wise dependence on kappa. And basically the lower bound tells us that this is something that's unimprovable. So let's see a little bit of this in action here. So what I've done here is I've plotted the trajectories of gradient descent and accelerated descent for different values of kappa. Now you can, again, the condition number kappa is equal to beta over alpha. And what I've done here is just minimize the simple quadratic. So beta, as we've seen, is equal to the largest eigenvalue, and alpha is equal to the smallest eigenvalue. This is again why, where this terminology comes in of the condition number. It's a standard definition in this case of the condition number of a matrix. So now let's look at what we have starting from small condition number. So small condition number is over here. A small condition number means that the largest eigenvalue and smallest eigenvalue are pretty close together. And what's plotted here is the trajectory of gradient descent and accelerated gradient descent, as well as the contours of the function. So first of all, you can see right off that the contours are very close to being spherical, which is what we would expect if the condition number is close to 1. You also observe that at least to the resolution of our ability to look at these plots online here, gradient descent and accelerated descent look pretty similar. So actually, if you look closely, you'll see that they're doing something that's a little bit different. They're not identical algorithms. That's to be expected that they're not identical, but it's always interesting to see where does an algorithm deviate from gradient descent. Remember, this is, gradient descent, again, is doing what is locally best. Ignoring everything else, it's just looking very locally and moving in the optimal direction, infinitesimally optimal optimal direction. So it's always interesting to see when something is doing something different from that. Now what happens as we increase the condition number? So you see that as the condition number increases here, the trajectories of gradient descent and accelerated gradient descent begin to look significantly different. And also what we're able to see, if you look at this, this lower row here of accelerated gradient descent, we're starting to see the impact of momentum. And we can see it in two ways. So first of all, note that in this first simple case, both gradient descent and accelerated gradient descent, not only are they similar in terms of the path that they follow, but they also seem to do about as well. They both get essentially to the optimal solution. But already by, say, the third column, or it's even more pronounced in the fourth and fifth column, you see that accelerated gradient descent in the same number of iterations is outperforming gradient descent. Now, I'm not providing all the details here of the simulation, but they're run for the same number of iterations, and they're both run for their optimal step size, which is 1 over beta. So you see that by the time that we get all the way to the right, where the condition number is very large, you can also see this again in the contours. You see how they're becoming very elongated. They're very far from spherical. We see two things. First of all, accelerated gradient descent is significantly outperforming gradient descent. But also, we start seeing increasingly pronounced overshoot, which is perhaps something else that we would expect from having this momentum term. Okay, so this illustrates a few of the different aspects of gradient descent and accelerated gradient descent. One thing you should also immediately notice is that gradient descent is always moving to a closer and closer and closer contour. And remember that we've showed this. We've showed that gradient descent is in fact a descent algorithm. It strictly improves at every single iteration until it gets to the optimal solution. But this is, again, not the case for accelerated gradient descent. So there are situations where accelerated gradient descent takes a step and it actually will increase the function value. Nevertheless, it is faster and it achieves the lower bounds. So in that sense, it's optimal. Okay, so now we're going to look at acceleration for smooth functions. And in this case, I'm actually going to go through I'm going to go through a proof to show you where the acceleration comes from. So the idea of acceleration is exactly the same. So we're going to incorporate momentum. So let's again start with a review here. Gradient descent is the update for gradient descent is equal to x minus my step size times the gradient of f of x. My momentum term, I'm going to denote by d. I guess I should put, so dt is equal to some multiple of xt minus 1. And I'm going to reserve the right to tune this multiple as a function of t. So let me write this a little bit differently. So this is my gradient step. So we can write our gradient descent algorithm is just xt plus 1 equals xt plus with this notation. And my momentum-based algorithm, and this specific flavor of momentum is called Nesterov acceleration, is x t plus 1 is equal to gradient descent, the gradient algorithm, but the gradient algorithm run on xt plus the momentum term. So in other words, xt plus dt plus. In other words, writing this out, so looking up here and writing out what xt plus 1 is, it tells me that it's equal to what's inside the parentheses minus a step size times the gradient of f evaluated at what's inside the parentheses. Now the reason I'm taking care to write this is to draw a distinction from the idea of doing gradient descent as before and then just adding momentum. So we're adding momentum before and then evaluating the gradient. Okay, so what do we know about our function f? So we're assuming throughout that f is convex and beta smooth. So we're going to use these two properties in order to show that this acceleration scheme gets us convergence that matches a lower bound. So we're going to show we match the lower bounds. In other words, what we're looking for is a 1 over t squared convergence rate compared to 1 over t for gradient descent. So what you're going to see now, the exposition of this proof was recently posted by Sebastian Bubeck. I should stop and make a general note about references. So there is a session in this class where I've explicitly discussed a few references that have influenced the exposition that we're giving here the most. But because this is directly drawn from Sebastian's blog post, I felt that it's appropriate to specifically highlight that at this point. But you can always look back to that lesson on references to get an idea of where everything is drawn from and what the key influences have been of this exposition. Okay, so again, what we have is that x t plus 1 is equal to xt plus dt plus, which is equal to xt plus dt minus my step size times the gradient of my function evaluated at xt plus dt. And recall that dt is my momentum term times some scalar that could be time dependent. So it's gamma t times xt minus 1. So what do we know about our function f? F is beta smooth. We're not assuming strong convexity in this case. And thinking back to our proof of 1 over t convergence for gradient descent, there were two things that we needed repeatedly, namely upper and lower bounds on f. That's basically what we know, beta smooth and convex. And so convexity tells me that f of x minus f of y is less than or equal to the gradient of f of x with x minus y. This is a lower bound on f of y, a linear lower bound on f of y. And because of smoothness, I also have a quadratic upper bound on f of y. And if we write y as the update, so f of y is less than or equal to f of x plus the gradient of f of x, y minus x, plus beta over 2 times y minus x squared. And if I write y as my one step of my gradient update, then we saw that this amounts to, as long as we take step size 1 over beta, we found that f of x plus minus f of x is less than or equal to minus 1 over 2 beta, times the gradient of f of x. Remember that this is, again, something that we've mentioned over and over again. This is a proof, this is a statement that gradient descent is in fact a descent algorithm, and this was the basis, the starting point for the proof. Okay, so I need a little bit of notation here in order to set things up. I'm going to let delta t equal f of xt minus f of x star. And of course, this is always greater than or equal to 0 because we're minimizing, and x star is the minimizer. I'm going to let gt equal minus 1 over beta times the gradient of f xt plus dt. And using this notation, we can see that xt plus 1 is equal to xt plus dt plus gt. So if you look at those with a definition of gt, this is immediate. There's two quantities that I want to bound. So we're going to use two inequalities that will basically rely on the property of convexity and this quadratic upper bound that translated into this descent guarantee. The first thing is that delta t plus 1 minus delta t is upper bounded by minus beta over 2. Beta is always here the smoothness parameter, times the norm of gt squared plus twice gt transpose dt. And dt plus 1 is by itself lower bounded by minus beta over 2 times gt squared plus twice gt dot product with xt plus dt minus x star. So let's see how where A follows from, and B follows very similarly from there. So I'll leave that for you. So again, we're trying to show inequality A, which is delta t plus 1 minus delta t is less than minus beta over 2 times gt squared plus 2 gt transpose dt. So where does this follow from? If I look at this right-hand side here, I can write this as minus beta over 2 times 1 over beta squared, this is just plugging in directly from the definition of gt, times the gradient of f of xt plus dt squared, minus 2 over beta times the gradient of f of xt plus dt transpose gt, transpose dt. All I've used here, again, is my definition of gt. So maybe I should remind you of this, that gt is equal to negative 1 over beta times the gradient of f of xt plus dt. Okay. This is equal to minus 1 over 2 beta. You can see this is just the product here, times the gradient of f evaluated at xt plus dt squared plus the gradient of f, xt plus dt transpose dt. This is just multiplying that out. And this is greater than or equal to f of xt plus dt minus eta times the gradient of f of xt plus dt minus f of xt plus dt plus f of xt plus dt minus f of xt. Whenever you see any inequality, to make sure that you're tracking what's happening, we should ask ourselves, where did this come from? And is this what we were expecting? So think about where these two inequalities came from. What did we use? Now, as a simple hint, when we don't know too much, when we only have a couple things, when we only know a couple things about our function, we probably just use those two things. So let me flip back 1 second so you can see the only two things we really know about our function. We know that it's convex, and we know that it's smooth, and therefore it satisfies something like this. So it's exactly those two properties that we used. And once this cancels, this is exactly the left-hand side. This is the left-hand side of A. So we've basically concluded A. Okay, let's keep going. So let me remind you, we've got A, which is delta t plus 1 minus delta t, is less than or equal to minus beta over 2 times gt squared plus 2 gt transpose dt. I've got something similar, delta t plus 1 is upper bounded by minus beta over 2 times gt squared plus 2 gt transpose xt plus dt minus x star. And I'm going to take a convex combination of these. So I'm going to take lambda t minus 1 times A plus 1 times B. And just adding these up, you'll see that what you get on the right-hand side, this is less than or equal to, because I'm adding two inequalities. Lambda is between 0 and 1, so I'm adding them with non-negative weights, so the inequalities can be added. This is less than or equal to minus beta over 2 times 1 over lambda t times xt plus lambda t dt minus x star plus lambda t gt squared minus xt plus lambda t dt minus x star squared. So when we look at this, we think about one of the main ingredients in all of the proofs that we've done has been to create telescoping sums. Now this is not quite there. This is not quite telescoping, but what if we could make it telescoping? Remember, there's a couple parameters that we haven't chosen. We haven't chosen lambda t. We haven't chosen gamma t. So let's write out what we would like. So we would like for the right-hand side to be telescoping. What does that mean? Let's just write out what we want and see if we can make it so. So in other words, writing out what's inside of the norm, I would like, so I want xt plus lambda t dt minus x star plus lambda t gt. So this is the first term inside, that's the first norm. I'd like for this to be equal to x t plus 1 plus lambda t plus 1 dt plus 1 minus x star. And you see that? So if that were the case, then I would exactly have this telescoping property between these two norms. So this is why I'm emphasizing this is something that I want. Okay, but now if we plug in what values of we have, we see that this is so remember, in other words, that dt plus 1 is equal to gamma t plus 1. I can write it as gamma t plus 1 of dt plus gt. So check that for yourself that this is the case. So using this is equal to xt plus 1 plus lambda t plus 1, and now I'm plugging in this expression for dt plus 1 that I have here. So plugging in what I just wrote, I have a gamma t plus 1 times dt plus gt minus x star, which is equal to xt plus dt plus gt plus this product of lambda t plus 1, gamma t plus 1 times dt plus gt minus x star. Now let's compare terms on the left and the right. We actually have a lot of similar terms. Again, we're trying to make the left and the right equal. So what do we need to make that work? This basically becomes, what we need here is for lambda t times dt plus gt to equal lambda t plus 1 gamma t plus 1 times dt plus gt. You see, these are the only two terms that are needed in order to make the left-hand side equal to the right-hand side. So how do we do that? Well, remember that gamma t is a parameter that I'm able to choose, as well as, and so is lambda t. Okay, so these are things that I can choose. So I'm going to choose gamma t plus 1 and gamma t to make this so. So we will just simply, gamma t is a parameter we choose. So let's choose it to make this equality true. So choose gamma t as a function of lambda t to make this inequality hold. Okay? And this is the key. So this is going to make this right-hand side telescoping. So let's make a definition here so that we don't have to remember exactly, we don't have to keep track of all of this notation. So let's define, and we'll only keep this onto the next page. So I want this that I just underlined times my minus beta over 2 to be, this is what's going to telescope. So let me call just this thing that I've underlined, not my minus beta over 2, let me call this 2 over beta times ut. And so once I multiply by beta over 2, then I'll just be left with minus ut. And therefore, by our choice of gamma t, and in order to make this telescoping, this must be equal to 2 over beta times u t plus 1. See? So basically what we have, once I multiply through by lambda t, is as follows. Remember that we had lambda t minus 1 times a plus 1 times b was less than 1 over lambda t times a bunch of stuff. This was on the previous page. Multiplying through by lambda t, this gives us, and plugging in for what a and b was, maybe I should remind you. So remember that a on the left-hand side was delta t plus 1 minus delta t, and b was simply delta t plus 1. So plugging in for those values for a and b and multiplying through by lambda t, we find that what we've got is lambda t squared. Here's my lambda t, and it's multiplied by this other lambda t. Lambda t squared times delta t plus 1, this is the delta t plus 1 from a, minus, I've grouped the terms together here, lambda t squared minus lambda t times delta t is less than or equal to these quantities that I just defined. ut minus ut plus 1. So we already did all our hard work. In the previous page, I picked gamma t to make this telescoping. This is what got me to ut minus ut plus 1. We're going to play exactly the same game on the left-hand side. Remember, lambda t is also a free parameter. Gamma t is a function of lambda t, but that still allows me to pick lambda t. Now, we're going to pick lambda t to make this telescope. So what do I need here? Note that I have, so let's write this out a little more clearly. We've got lambda t squared times delta t plus 1 minus lambda t squared minus lambda t times delta t. You see, I already have my delta t plus 1 minus delta t. I just need to make sure that the coefficients work out. What do I need? I simply just need the coefficients to be exactly the same. So we need lambda t squared minus lambda t to be equal to lambda t minus 1 squared. Because in that case, I'll have lambda t squared delta t plus 1 minus lambda t minus 1 squared delta t. That's exactly what I need for telescoping. Okay, so specifically, we can see is if we have lambda t approximately equal to t will satisfy this. So you can think about lambda t as scaling with t, but we can easily derive this recursion. So specifically, what we need is lambda t is equal to minus 1 plus 4 lambda squared t minus 1 divided by 2. So we can actually solve it, but really it's important to think about how lambda t scales. It's scaling about approximately like t. Okay, so if indeed I have something that's telescoping, then what are we left with? Now, I'm going to sum both sides. And what do I find? I'll be left with, on the left-hand side, lambda t, capital T squared, I'm going to sum it for t iterations, times delta t plus 1 minus lambda 0 squared times delta 1. So I summed and all of the terms on the left telescoped. Less than or equal to ut minus ut plus 1. If I sum that, it will be just the first term minus the last term. Remember that all of these terms are non-negative, so this is certainly less than or equal to not subtracting ut. So just subtracting 0. And what does this tell me? This leaves me with delta t plus 1 is basically less than or equal to some constant u0 plus lambda 0 squared delta 1. So this is a constant that doesn't particularly matter, divided by lambda t squared. Let's unwrap a little bit so you can remember what the basic definitions are here. Remember that delta t was exactly what we cared about. It's our suboptimality. So after all this work, delta t is equal to f of xt minus f of x star. And remembering how lambda t scales, basically what this is saying is our desired result. So in other words, our error, our suboptimality, f of xt minus f of x star, scales like 1 over t squared. So this is exactly the improved rate that we were hoping for. So this concludes the basic outline of the proof. And we've now seen that the lower bounds are matched by accelerated gradient descent. The key thing that we needed for accelerated gradient descent was this concept of momentum. So to wrap up the session, we saw that the lower bounds for smooth convex optimization are matched by this idea of gradient descent plus momentum. A final comment is that we did have to work quite hard to choose the coefficients carefully. So this seems to be important. So we now have matching upper and lower bounds. And this concludes this section. We'll pick it up next time.